Hello, everyone. Today, I would like to present our work on CLERA, a unified model for joint cognitive load and eye region analysis in the wild. This work was done with my wonderful colleagues at MIT. First, let's talk about the background and motivation. In cognitive psychology, cognitive load refers to the used amount of working memory resources, and it has been shown in many studies that cognitive load has a high impact on people's decision-making. For example, if someone is put into high cognitive load status by memorizing many digits, like 7 digits, it will more likely to choose cake rather than fruit as a dessert. And there has been many work in recent years on non-intrusive cognitive load estimation. The question here is, how do we measure the state of the human mind, such as cognitive load? And the answer is that video-based metrics, such as the pupil movement, can capture the various characteristics of the psychological reactivity and movement of the eye, and in response to varying cognitive load. And here is an example of the non-intrusive cognitive load estimation. And in prior work, people usually use an eye tracker to capture the eye image sequence. And the first one approach is that we extract the pupil position from the eye image and then use some sequential modeling, such as hidden Markov model, to predict the cognitive load classification. And a more recent approach is that we use deep learning methods, such as 3D convolutional neural network, to directly predict the cognitive load status with the input of eye image sequence. And there are many potential issues with the prior method, and we have two motivations here to motivate our work. The first one is there is likely exist some redundancy in computation, and we can potentially reduce that. For example, in an online application environment, when you are using an eye tracker, it needs to potentially compute some visual features to track the eye. And then when you have the output eye image sequence from the eye tracker, if you take the first approach that you extract the pupil positions, it also needs to compute visual feature. And if you use a deep learning model to predict the cognitive load, you still need to compute the visual feature. So there's a redundancy in computation here. And second problem is that it's about the model complexity and generalization. So in the first approach, it is very easy to collect the data of the pupil position, and you can collect it at large scale. But it is a very simple abstraction of the eye movement. And if you just use the movement of the pupil position, you might lose some useful information. However, on the second approach, if you do it end-to-end with a deep learning model, the high-dimensional raw image input is very complex, and you need a large-scale training data to train a model that captures the eye movement from the raw image to predict the cognitive load classification. However, it's very hard to collect the cognitive load classification data in practice. And that motivates our work. I will talk about the methodology of CLERA, a unified model for joint cognitive load and eye region analysis. So our approach extends the previous deep learning framework. So we first have, say, an image model for feature extraction. So given an image sequence, we have the frame level deep feature map from a backbone image recognition model. And then we first perform detection of the eye on that frame level deep feature map. And we can get the bounding box of the eye. And we can also predict the blink with the detection task data. And then after that, the architecture extends to two different heads. One is for localized feature tracking for cognitive load estimation over time. And the second one is mask localized regressor for eye landmark detection. And we will dive into the details of those two heads. So first, for the localized feature tracking, we use a temporal tracking method, considering the temporal displacements using the IOU, meaning that if we have a bounding box that overlaps largely between two frames, then we think they are probably tracking the same eye. Then we use that then we say it establishes the tracking. And for those successfully tracked eyes, we further extract the localized feature vectors by locating the feature vector on the feature map using the location of the tracked eye. And then the localized features tracked through frames are then used as input for the temporal modeling. Here we use a very simple convolutional 1D convolutional model to do the temporal modeling. But the key here is that we can use the same feature not only for the eye detection, but also for temporal tracking, and then to do the cognitive load classification. And secondly, for the precise eye landmark detection, we design a mask localized regressor to address the limitation of coordinate precision in mask-based keypoint detection approaches. And here's a description of the method. So our method adds another branch of keypoint offset regression. So this branch predicts the keypoint agnostic offsets, which are then added to the mask to predict the indices to get the precise coordinates. This is because if you just take the indices, it is usually the integer of that has low precision. But if we add the regressor offset, we can have the flow point keypoint coordinates, which gets you to higher precision, better than the not limited by the resolution of your input image. And then let's discuss the new dataset we call it MIT pupil dataset. So this is a large-scale pupils and blinks dataset, which is comprised of 28,000 images, each with the following attributes. First is the state, which is either open or closed eyes, and the bounding box of the eye. And then we have the eye landmarks, which are the lateral and medial cancers, and also the pupil position. And this is a comparison of our dataset comparing to other open source datasets. And we can see that our dataset is the largest dataset that has the internet image, which are very wild with different camera views and the different environments and the backgrounds. And we have the largest number of images annotated with both open and blink eyes. And each of all the images are annotated with pupil and landmarks. And here's an annotation interface. So the thing to highlight here is that our annotation interface gets you the flow point precision of the key points and the bounding box positions. And we also did the two-pass annotation validation. So each image is annotated by two different annotators, and we only keep the data that we have the agreement upon two different annotators. And we have some quality control statistics reported in the paper. And also one thing to mention here is that our dataset only captures the single eye annotation. And this is designed in purpose because we designed the training methodology to work with these kinds of single eye annotation images. So simply put, we can infer the region where potentially the other eye exists by using the position of the current eye. Because if you have the bounding box of the eye, you probably know what's the region that the other eye may exist. And then we can generate a gradient mask to ignore that region or ignore the loss in that region when training the model. And then that results in, if our model is only trained on a single eye, it also generalized to detect both eyes in test time. And by doing this, we can easily double the amount of annotation within the same cost of annotation. And finally, let's discuss some experiments and results. So here's so first for the cognitive load estimation, we use an unpublished dataset obtained and extended from prior work when we have 30-second video clips of driver faces, each under one of two different cognitive levels. So there are like low and high cognitive levels. And the cognitive low levels we use the MBAC task to put drivers into different cognitive load levels. And here's the video footage of the data set we use for cognitive load estimation. And we can see that the results of our pupil and eye landmark detector is very accurate, and it can also handle some very tricky situations, such as very bad lighting conditions, but still get very robust performance. And the results show that our proposed method outperforms previous work and shows significance of using the localized feature tracking. And we can see the classification accuracy is better than our previous methods. And also our method runs in real time, and we will discuss more in later slides. Then here is the results for the eye landmark detection. We can see that our method significantly outperforms the baseline methods on the eye landmark prediction task, and it runs in real time. And we also perform a cross dataset evaluation on the MT2 gaze dataset. And we show that similarly, our method also outperforms the baselines. And one thing to highlight here is that the baseline mask is actually the mask RCN implementation on this dataset. And we see that our method outperforms that and also has the very high real-time performance. And here are some visualizations of the predictions on the testing set of our dataset. You can see that our dataset captures a lot of variation in all kinds of like images from the web. And we also show some failure cases because the images are maybe quite difficult to predict, and there is still some space for improvement in the future work. And also here's the visualization on MT2 gaze dataset, and we see that these datasets are more clean and easy to predict, and we have better performance on these datasets. And finally, we also evaluate the performance on the blink detection task using also another cross dataset validation on the RTB and E dataset. We use the whole dataset as the testing set. And we can see that our model shows competitive performance on blink detection. And more importantly, our model is a single model that handles all the different eye, blink, and landmark detection tasks, and it still runs in real time with input image at 2 times higher resolution than the numbers reported here. And finally, we have some discussions and limitations. So for discussions, we have shown that by using a unified model, we can perform multiple tasks at almost no additional computation cost compared to the standard eye tracking method. And we can see that CLERA also outperforms prior task-specific models in eye landmark detection, blink detection, and also the cognitive load estimation. So in the broader context of the whole HCI research, we hope our work can inspire further investigation into more unified modeling of different HCI or human factors tasks rather than focusing solely on a specific individual task. For example, if you think the physiological reaction of the eye region is important to your task, and then you probably can combine your task with some other eye region analysis method, and maybe they can work well together and without any additional computation cost. And our method also has many limitations. So first, our dataset used for cognitive load estimation includes varying lighting conditions and camera placement, which has shown to have an impact on the accuracy of the models. For example, we implement 2 comparison methods and find that both methods experience a decrease in the accuracy from above 80%, which is claimed in prior work, to around 60% on our dataset. So that means while our method for cognitive load estimation shows a significant improvement, it may not be appropriate to use it directly in its current form for real-world tasks due to the performance and safety concerns. In our study, our study focused solely on the specific type of cognitive load estimation using the eye dynamics, and we did not explore other possible approaches such as other physiological signals such as heart rate and other like ECG type signals. And there has been some ongoing work showing that a combination of both the eye dynamics and physiological signals could further improve the accuracy of the detection. And finally, I would like to thank you everyone for your attention. And this work is in part sponsored by Pioneer. And I also want to thank to my wonderful colleagues for collaborating with this work. And I'm happy to take questions.